A heterocycle is a ring that contains atoms of more than one element. Common organic heterocycles are comprised of carbon and either nitrogen, oxygen, or sulfur. Consider, for example, the structures of Viagra and Nexium. Both of these compounds contain nitrogen heterocycles that are highlighted in red here. Many different kinds of heterocycles are commonly found in the structures of biological molecules and pharmaceuticals. We're going to take a look at a few simple heterocycles in this video. Pyrrole is a 5-membered aromatic ring containing one nitrogen atom, and it's numbered starting with the nitrogen atom. Now, as we saw in chapter 17, the lone pair of this nitrogen atom participates in aromaticity and is therefore significantly less basic and less nucleophilic than a typical amine. Pyrrole undergoes reactions that are expected for an aromatic system, such as electrophilic aromatic substitution. In fact, pyrrole is even more reactive than benzene, and low temperatures are often required to control the reaction. Electrophilic aromatic substitution occurs primarily at carbon-2 because the intermediate formed during the attack at carbon-2 is stabilized by resonance. When the attack takes place at carbon-2, the intermediate has 3 resonance structures. In contrast, when the attack takes place at carbon-3, the intermediate only has 2 resonance structures. An imidazole ring is like pyrrole but has 1 extra nitrogen atom at the 3 position. Histamine is an example of an important biological compound that contains an imidazole ring. Pyridine is a 6-membered aromatic ring containing 1 nitrogen atom and is numbered starting with the nitrogen atom. The lone pair of the nitrogen atom is localized and occupies an sp2 hybridized orbital, and as a result, pyridine is a stronger base than pyrrole. Nevertheless, pyridine is still a weaker base than alkylamines because the lone pair occupies an sp2 hybridized orbital rather than an sp3 hybridized orbital. By occupying an sp2 orbital, the electrons of the lone pair have more s character and are therefore closer to the positively charged nucleus, rendering them less basic. Since pyridine is an aromatic compound, we would expect it to exhibit reactions that are characteristic of aromatic systems. In fact, pyridine undergoes electrophilic aromatic substitution reactions. However, the yields are generally quite low because of the inductive effect of the nitrogen atom, which renders the ring electron poor. High temperatures are required, as we see here. We need 300 degrees Celsius in order to brominate our pyridine and make 3-bromopyridine. And the reaction only proceeds in a 30% yield. Pyrimidine is similar in structure to pyridine, but contains 1 extra nitrogen atom at the 3 position. Pyrimidine rings are very common in biological molecules. Pyrimidine is less basic than pyridine due to the inductive effect of the second nitrogen atom.